Okay, so Chapter 12 of Introduction to Networks is IPv6 addressing. So, of course, we looked at IPv4 Friday, and so we're having a look at similar things in IPv6, but of course they have redesigned IPv6, so not everything's identical. And so first thing we're going to look at is some problems that have been identified in IPv4 that they wanted to fix for IPv6. And so then we're going to look at how IPv6 addresses are represented or displayed, and also how we can abbreviate them a little bit to try and make them a little bit shorter. And so we're also going to look at the different types of IPv6 addresses, much the same as we've looked at the different types of IPv4. And then we're going to look at global unique addresses, or GUA, as well as linked local addresses. And then we're going to look at dynamic addressing for the global unicast addresses. Okay, and we're also going to look at dynamic addressing for IPv6 with linked local addresses. We're going to look at multicasting, and we're also going to look at how we can subnet IPv6. And thankfully, that's one bit that we really don't talk a lot about because it's not very complex at all. So, what issues are there with IPv4? So, of course, the major one for IPv4 is it's run out of addresses. And so that's the major reason why IPv6 exists, is because, as I've probably said a few times, 4 billion addresses for 7 billion people doesn't work very well. And so the development of IPv6 also included fixes for some other limitations for IPv4 and enhanced its abilities. So with an increased internet population, the limited IPv4 space, issues with NAT and Internet of Things, the time had come to begin the transition to IPv6. I must admit, this transition is going at glacial speed. IPv6 has been out for more than 20 years, and we're mostly still on IPv4, at least in Australia we are. It's just going so slowly. But anyway, so IPv4 and IPv6 at the moment coexist. And so because IPv6 does not cover the world yet, not everyone's using it. And so IPv4 is still the major player. And so they will need to coexist until everyone has transitioned fully to IPv6. And so the Internet Engineering Task Force has created various protocols and tools to help network administrators migrate their networks to IPv6. These migration techniques can be divided into 3 major categories. So dual stacking is where hosts have both IPv4 and IPv6 running at the same time. Tunneling is where you can actually tunnel IPv6 packets through an IPv4 network. And so basically it adds another layer of encapsulation. Basically, we're going to encapsulate an IPv6 packet into an IPv4 packet. And so and then there's translation as well. So there is some NAT between that's used in IPv6 and allows IPv6 enabled devices to communicate with IPv4 enabled devices using a translation technique similar to NAT for IPv4. So note, tunneling and translation are for transitioning to native IPv6 and should only be used where needed. The goal should be native IPv6 communications from source all the way to destination. Okay, so IPv6 representation. So, of course, as we've said before, IPv6 addresses are 128 bits in length and are displayed in hexadecimal. IPv6 addresses are not case sensitive, and so there's no difference between a capital or a lowercase a through to F, no difference at all. And so it doesn't matter which way you write it. So the preferred format for writing an IPv6 address is basically 4 hexadecimal characters separated by a colon, then another 4, etc., etc., etc. And so of course, 4 hexadecimal characters course, 4 bits each, so it's actually 16 bits for each colon there, and so they call that a hextet. So it's an unofficial term used to refer to a segment of 16 bits or 4 hexadecimal values. And so some examples of IPv6 addresses are below, and so you can see that there's 4 characters, a colon, 4 more characters, etc., etc., etc. Now this is basically the addressing done in longhand. You can shorthand these addresses as well, and we will talk about that later in the slides. Now, there's one way we can shorten things instantly is we can actually omit any leading zeros within a hextet. And so 01AB can be represented as 1AB. 09F0 can be 9F0. You can't do trailing zeros, but you can do leading zeros. So 0A00 still needs to be A00, but 00AB can just be AB. So basically, because there's a hextet, it gives you a placement, and so if there aren't 16 characters worth of hexadecimal characters there, we'll just fill up the front until it is 16 with zeros. So that's a very quick and easy way of shortening these things. And so as you can see, you can shorten this address here down to this quite easily. Quite a discussion going on outside. Okay, now there is also the double colon. And so a double colon can replace any single contiguous string of 1 or more zeros, or hextets that consist of all zeros. And so we've got an example here that we've already done the leading zero shortening. And so we could actually shorten it even further. All right, so as you can see here, we've got this double colon. And so that's replacing all of these zeros, this big long string of zeros. You can only do this once in an address though, because basically when you try and interpret this, you start at the beginning with this and you start at the end with that. And then once you've finished putting them in, you just fill the gap with zeros. If you did it twice, well, how many zeros go in the first one and how many zeros go in the second one? You can't figure that out. And so that's why we can only do it once. So we can still get rid of leading zeros, but oh, we've got security up here as well. All right, so there are different IPv6 address types. And so there's Unicast, Multicast, and Anycast. Now, Unicast, of course, is much the same as a Unicast address with IPv4. And so it's uniquely identifies an interface on an IPv6 enabled device. A multicast is used to send a single IPv6 packet to multiple destinations. Again, the same as a multicast in IPv4. So an Anycast is different, and it's not really the same as a broadcast because IPv6 doesn't have broadcasts. Basically, multicasts have expanded to take over from broadcasts, and so Anycast is a little bit different again. So this is an IPv6 unicast address that can be assigned to multiple devices. A packet sent to an Anycast address is routed to the nearest device having that address. All right, so unlike IPv4, IPv6 does not have a broadcast address. However, there was an IPv6 all nodes multicast address that essentially does the same thing. So as I said, multicast has expanded to take over the job of what broadcasts do in IPv4. Okay, so prefix length. So we don't do a subnet mask in IPv6, we do the slash notation. And so, of course, that's called the prefix length. And so it's used to indicate the network portion of an IPv6 address, And so basically, the typical one that you will see is actually /64, which means the first 64 bits are network number, the last 64 bits are host number. And so, of course, it can vary to be different to that, but it won't vary often. So it's strongly recommended to use a 64-bit interface ID for most networks. This is because stateless address auto configuration uses 64 bits for the interface ID. It also makes subnetting easier to create and manage. So we will talk about how subnetting does happen. Of course, that's the last topic in this slideshow. So first half of the address is network number, second half is host number, or interface ID they call it. Okay, now type of unicast addresses. Unlike IPv4 devices that only have a single address, IPv6 addresses typically have two unicast addresses. And so there is the global unicast address, and so this is of course the one that's assigned to you from an ISP or whoever it may be, and these are globally unique, and that's of course what you connect to the internet. Now, hosts will often also have a linked local address required for every IPv6 enabled device and is used to communicate with other devices on the same local link. And so linked local addresses are not routable and are confined to a single link. So if you remember last time we spoke about Ipv6 addresses, that 169.254 address that a host can get if it can't find a DHCP server. Well, this is sort of mostly equivalent to that. But the difference is with Ipv6 typically only ever happens with Windows, and also it only ever happens if there is no DHCP server. With IPv6, they actually always have a linked local address. Every host that's got IPv6 will have a linked local address. And that is what is used to talk to hosts on the same subnet. All right. Now, so here is a bit of a breakdown of your unicast addresses. And so there's global unicast, and so that's the public IP addressing. Linked local, and they all start with FE80 as the first 4 characters in their address. There is also the loopback address, and it's : 1. So if you remember the loopback in IPv4, it's 127, and we actually wasted 16 million addresses to do that. Well, we've used one address for loopback in IPv6. And so that can also be used as an unspecified address. And there are unique local addresses as well, which are sort of like the private addressing range that we use as well. So the 192.168s, the 10s, the 172.16s. And so these are unique locals, and so you can use those addressing as well as much as you like. And then there's embedded IPv4, so that's basically a part of the addressing range that's been set aside just to be able to relate directly to the IPv4 range. So of course that can probably be reassigned to do some other task once IPv4 is gone. How long that will take is another thing. A note about the unique local address. IPv6 local addresses, so these ones here that I was talking about, have some similarity to those private addresses that I said, but there are significant differences. Unique local addresses are used for local addressing within a site or between a limited number of sites. Unique local addresses can be used for devices that will never need to access another network. Unique local addresses are not globally routed and translated to a global IPv6 address. Many sites use private nature of RFC 1918 addresses to attempt to secure or hide their network from potential security risks. This was never the intended use of the unique local addresses. Okay, now, when you have a global unicast address, there's actually 3 parts to it. So currently only GUAs with the first 3 bits of 001 through to or 2000 are being assigned. Currently available GUAs begin with a decimal 2 or a 3. This is only 1/8 of the total available IPv6 address space. Now, basically what happens is if you get any addressing from an ISP, you actually get a /48 number from them. And so that's what this global routing prefix is. And this subnet ID here is actually another 16 bits. So of course, add them together, that's what ends up being the 64 bits. And this bit here is actually what we do the subnetting with, which we'll talk about a bit later. Of course, this interface ID is the last 64 bits. And so, yeah, so that's basically how it goes. And so with your 001s, it goes from 001 all zeros through to 0011. And so basically, so of course this is in binary, and of course this is displaying it in hexadecimal. All right, so the global routing prefix is the prefix or network portion of the address that is assigned by the provider, such as an ISP, or to a customer or site. The global routing prefix will vary depending on ISP policies. And then the subnet ID field is actually the area between the global routing prefix and the interface ID, and it's used by the organization to identify subnets within its site. So 16-bit number, 2 to the power of 16, you've actually got 65,000 possible subnets you can create. So there is a lot more addressing space with IPv6. And so of course the interface ID, is equivalent to the host portion of an IPv4 address. It is strongly recommended that in most cases /64 subnet should be used, which creates a 64-bit interface ID. Now IPv6 allows the all zeros and all ones host addresses to be assigned to a device. The all zeros address is reserved for the subnet router Unicast address and should be assigned only to routers. Okay, so the link local address enables a device to communicate with other IPv6 enabled devices on the same link and only on that link. Packets with a source or destination link local address cannot be routed. Every IPv6 enabled network interface must have a link local address. If a link local address is not configured manually on an interface, the device will automatically create one. And so IPv6 link local addresses, as I said, start with FE80. And so routers use LLA to neighbor routers to send routing updates. Hosts use LLAs of the local router as the default gateway. Okay, so how do we do static configuration of the global unicast and link local address on a router? So static global unicast address. The most IPv6 configuration and verification commands on iOS are very similar to the IPv4 counterparts. In many cases, the only difference, instead of it being an IP command, it's an IPv6 command. So the command to configure IPv6 address is IPv6 address, and then you specify the address, and then you do the /number. So here's an example here. IPv6 address, you specify the address, and then you do /64 for the network prefix. And then, of course, you need to turn the interface on, as you always do. Now, of course, on a host, you can do it statically as well. And so basically use the following IPv6 address. Again, you can specify it. You can see that there's a double colon there. Prefix length there, and then the gateway for that subnet there. And so apart from the addressing being different because it's IPv6, it's very much similar to IPv4. So manually configuring the IPv6 address of a host is similar to configuring IPv4. The global unicast address or link local address of the router interface can be used as the default gateway. Best practice is actually to use the link local address. Note, when DHCP version 6 or SLAAC, which is stateless automatic address configuration, the LLA of the router will automatically be specified as the gateway address. All right, so configuring the link local address lets you create an address that is recognizable and easier to remember. So link local addresses can be configured manually using the IPv6 command. You just need to put the link local on the end, you also don't need to supply a prefix length with a link local address. So the example shows the command to configure an LLA, and so IPv6 address FE80::1:1. Note the same LLA can be configured on each link as long as it's unique on that link. Common practice is to create a different LLA on each interface of the router to make it easy to identify the router on the specific interface. So this could be router 1, interface 1. Then you could do 1 and 2, and then 1 and 3 for all the other interfaces. I think that's what the plan is that they're getting to. All right, dynamic addressing. Now this is somewhere that IPv6 is much better than IPv4. So devices obtain global unicast addresses dynamically through ICMP version 6. Now, I think we might have mentioned these briefly before. Router solicitation and router advertisement messages are used. And so instead of a DHCP discover message, which is what an IPv4 host does when it wants a dynamic address, a IPv6 host actually sends out a router solicitation. So, hey, is there a router out there? That's basically what it's saying. And it's multicast, and only routers will listen for the destination address that multicast is sent to. So a router will reply with a router advertisement, and that's sent by routers to inform hosts on how to obtain a global unicast address. Now, there's more than one way that can go, and you can configure the router to respond differently. And so the information they can get is network prefix and prefix length, default gateway address, and also they can get DNS addresses and names. Now, the router advertisement can actually specify 3 methods for configuration. So SLAAC, that's it alone. And so the router says, by the way, you belong to this network with this prefix. Figure out your interface ID yourself, but you know what network you're connected to. Now, that's great, except the router rarely tells them the DNS server. So that's a bit of a downside. But you can actually have SLAAC with a stateless DHCP server. And so, of course, the addressing is done on a per interface basis. That works nicely. But with the stateless DHCP server can then supply other information. And so this information could well be great for all of your subnets, not just one subnet. And so DNS server and address could be part of that information. Another option is to say that we're not using SLAAC at all, just do DHCP. So with SLAAC, it allows the device to configure its global unicast address without the services of DHCP. And so they get the necessary information from their router advertisement. The prefix is provided by the router advertisement. The device uses either EUI64 or some random number generation method to create their own interface ID. So EUI64 is what was most common when IPv6 first came out, and I think Cisco still uses it. Now, if you're using Windows, if you've got Windows XP running IPv6, it's still used EUI64, but newer versions of Windows actually do a random number generation process. Now, with SLAAC, with stateless DHCP, the addressing is done all the same, but it also sends a little message saying, if you send out a DHCP request, you'll actually get some more information as well. And so the host will send out a DHCP request or DHCP solicit message, and then the DHCP server will respond. And typically it's DNS information that, of course, it's not normally going to get from a router. And then the stateful DHCP version 6 is basically the same as DHCP for version 4. And so the router advertisement message says, I'm not going to tell you anything, send it a DHCP request to get all of your information. And so from there, you then go through router. So you do router solicitation. The reply is, well, I'm not going to tell anything, and so then it has to send out a DHCP solicit message to actually confirm, to get its details from the DHCP server. Okay, now the EUI64 process versus random, I'm going to say 6 of one, half dozen the other. As long as you get a unique number, it doesn't matter. Now, EUI64 is basically, it uses the MAC address and then jams some extra bits in the middle. While the random, it's just a completely randomly generated number. So EUI64 is from the IEEE, and it's the extended unique identifier. And of course, it's 64 bits long. And so a 16-bit value of FFFE is actually inserted in the middle of the MAC address. And so basically you get the first 24 bits of the MAC address, then that FFFE, and then the last 24 bits of the MAC address. So the 7th bit of the client MAC address is reversed from binary 0 to binary 1, and away you roll. When it comes to randomly generated device, so depending on the operating system, the device may use a randomly generated interface ID instead of the MAC address. Beginning with Windows Vista, Windows uses a randomly generated interface ID instead of one created using EUI64. To ensure the uniqueness of any IPv6 unicast address, the client may use what's called a DAD message, or duplicate address detection. This is similar to an ARP request for its own address. If there is no reply, then the address is unique. So basically, it will invent its own IPv6 address. Then it will actually send out a neighbor solicitation message for itself saying, hey, is there anyone using this IP address? And so if no one answers, well, no one must be. And so that's all good. It must be a unique number. All right. So dynamic addressing for IPv6 linked local addresses. And so again, basically it's the same process as we did for the global unicast addresses. So all IPv6 interfaces must have an IPv6 linked local address. And so they are configured dynamically. And so of course they all start with FE80, and then the last 64 bits are, of course, either going to be EUI64 or randomly generated number again. And so normally the host will actually use the same interface ID for both the GUA as well as their LLA. And I think that's what this slide is showing us here. So operating systems such as Windows will typically use the same method for both SLAA created GUA and also the dynamically assigned LLA. So if you look at the the global unicast address and the linked local address, the host section will often be identical. And so this is EUI64. This is just a pure random number. Why randomize twice when you don't need to? So Cisco routers automatically create an IPv6 linked local address whenever a global unicast address is assigned to the interface. By default, Cisco routers use EUI64. Here is an example of a linked local address configured for G000 on router 1. And so you can see there's FE80, and then there's the MAC address plus that FFFE jammed in the middle. Okay. Cisco routers automatically create an IPv6 linked local address whenever there's a GUA assigned. By default, is that the same as the previous slide? Yeah. Okay, so multicast addresses. IPv6 multicast addresses have the prefix FF00/8. There are two types of IPv6 multicast addresses: well-known multicasted and solicited node multicast addresses. Again, much the same as IPv4. Multicast addresses can only be a destination address, not a source address. So these well-known multicast addresses are for specific purposes. So the first one is actually all IPv6 hosts. The next one I think is all IPv6 routers. And then there are other ones that are used specifically for IPv6 routing protocols and other such things like that. The solicited node ones are more the ones that are used by other processors completely. So, again, you might use it for rolling out multiple host operating systems using multicast, or of course it could be some kind of broadcasting process for video or something like that as well. They're the most common uses of multicast. Okay, so well-known IPv6 multicast addresses are assigned and are reserved for predefined groups of devices. So as I said, there's an all nodes, so this is all IPv6 hosts will listen to this. And so when you do a neighbor solicitation message, the destination will be FF02::1. And then when you do a router solicitation message, it will actually be FF02::2. That will be the destination. And so, yeah, that's basically the process. A solicitor node multicast address is similar to an all nodes multicast address. A solicitor node multicast address is mapped to a special Ethernet multicast address. The Ethernet NIC can filter the frame by examining the destination MAC address without sending it to the IPv6 process to see the device is the intended target of the IPv6 packet. So basically in software, when IPv6 is interested in a multicast, it will actually tell its NIC, oh, by the way, I'm interested in this multicast, and so the NIC can then deal with whether it wants that multicast or it doesn't. With broadcasts, of course, it always has to go up into software. So multicast can be dealt with on the NIC more completely than broadcasts can. And that's the major reason why they've killed broadcasts. Okay, so how do we subnet an IPv6 network? I think I've already given you the hint. We have the separate subnet ID field. And so as I said, the first 48 bits that you get from your ISP is actually that global routing prefix, and the rest is actually what you can actually play with and create subnets with. So 65,000 subnets should be enough. And so with that, normally it's all set to zeros, but of course you can actually start adding in extra numbers to that and subnetting it basically. So given an address of 2001 DB8 ACAD::/48, as I said, you can have 65,000 subnets. This global routing prefix is the same for all subnets. Only the subnet ID hextet is incremented in hexadecimal for each subnet. So first subnet can be all zeros. Then you got 1, 2, all the way up to 4 Fs. Lots of options. So the example topology requires 5 subnets, 1 for each LAN, as well as for the serial link between R1 and R2. So the 5 IPv6 subnets were allocated with the subnet ID field of 0001 through to 0005. Of course, they're all /64, and so that works nicely. So as you can see, there's a CAD1, a CAD2, a CAD3, a CAD4, a CAD5. Very nice. So how would you address that? Well, basically, you just need to do the different interfaces with the different subnet ID there, 1, 2, and 3 in this case. Not at all tough. Thank God we've hit the end of the topic. So, what did we talk about? So as I said, IPv4 has a theoretical maximum of 4.3 billion addresses. Not all of those are usable, of course, but anyway, and there are 7 billion people on the planet. So instantly we have a problem. And so, of course, IPv6 is there to fix that problem. And so, of course, the IETF has created various protocols and tools to help network administrators migrate from IPv4 through to IPv6. And so the major categories are dual stack, tunneling, and translation. IPv6 addresses are 128 bits in length and written hexadecimal. The preferred format, of course, is 16 hextets with a colon between them. There are three types of IPv6 addresses: Unicast, Multicast, and Anycast. But of course, there are subcategories as well. An IPv6 unicast address uniquely identifies an interface on an IPv6 enabled device. The IPv6 global unicast address are globally unique and routable on the IPv6 internet. IPv6 linked local addresses enable a device to communicate with other IPv6 enabled devices on the same link, but only on that same link. The command to configure a global unicast address is the IPv6 address command. The device obtains a global unique address dynamically through an ICMPv6 message. And so, of course, that's a router solicitation followed by a router advertisement. IPv6 routers periodically send out those router advertisements every 200 seconds. So it keeps all the hosts up to date, basically. And so RA messages have three possible versions. And so there's fully automated with stateless DHCP server, or completely DHCP server. The interface ID can be created either by the EUI64 process or a randomly generated number. EUI process uses this 48-bit MAC address and then inserts another 16 bits in the middle to get the interface ID. Depending upon the operating system, a device may either use EUI64 or a randomly generated interface ID. All IPv6 devices must have a linked local address, and again, that can be either manually or dynamically created. Cisco routers automatically create a linked local address whenever they have a global unicast address. And so with multicast addresses, there's two types. There's a well-known multicast for specific purposes, or solicited no ones for ones that other purposes you may have. Two common IPv6 assigned multicast groups are FF02:1, which is all IPv6 hosts, or FF02:2, which is all routers. And that's, as I said, they're the destination addresses for neighbor solicitation or router solicitation in order. A solicited node multicast address is similar to all nodes multicast address. The advantage of solicited node multicast address is it's mapped to a special Ethernet multicast address. IPv6 was designed with subnetting in mind, and there's a separate subnet ID field as part of the globally unique unicast address. It's used to create those subnets. There's the logo. So that's it for chapter 12. We'll see you in chapter 13 later.